Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that give you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, and today I would like to dedicate this episode to the people that are developing space systems for the colonization of the space, but only to the people that are using ROS-based robots. If you are involved in this progress of humanity, then this episode is dedicated to you. And today we are going to learn more about space and ROS. But before that, let me tell you that if you want to learn about the building fleets of robots using OpenRMF, then you have to attend the Managing Fleets of Robots with ROS2 online training that at the Construct we are organizing. In this workshop, you will learn how to make multiple robots navigate in a ROS2 environment and how to use the Open RMF to manage different fleets, how to coordinate them, how to decide which robot serves which task, when to go to refill the batteries, open the doors, and the robot command, and many other things. This is a live online training, but all the lessons are practice-based with both a simulation and a real robot. And they are also teacher-led. We have even created a cafeteria there in Barcelona to which you will connect remotely from your location and do your practice with those robots. So forget about passive listening to a video lecture and instead actively practice at the construct. And remember that everything is running from your web browser, so you don't need to install anything on your computer. You will start the practice with robots from minute one with the construct. Okay, and then having said that, I will put a link on the show notes below in order to find this training, so you can go and find it. But now I think that it's time that we go and we start talking about the meat of this podcast episode, right? That's why you are here listening. So it's my pleasure. Let me introduce you to Alex Sowell and Misha Savchenko. Alex and Misha work on the Dexterous Robotics Team at NASA's Johnson Space Center. Alex is the technical lead for robotics at CACI International, and Misha is software lead at METECS. They both work together to build the next generation of robots for NASA. Welcome to the podcast, Alex and Misha.
It's a pleasure. Thank you, Ricardo.
Thank you for having us.
Yes, my pleasure. Yeah. So when there is more than one people in the interview, we don't know who goes first and who have this conversation, and especially when we are also online, it's a little bit more difficult. It's funny, right? Have you been interviewed in other podcasts before?
I think this is my first one, so we'll see.
Same for me.
Okay, very good. Very good. So I hope that you are going to enjoy. And this is a conversation between, let's say, friends, even if it's the first time that we meet, but that's the spirit of the conversation. But I would like to, as I have mentioned a lot of details there when I introduce you both, but maybe the audience, I was worried. I told you that I was worried that the audience, maybe they don't get everything because we understand about NASA, but I have explained a lot of names of other things. So for example, in your case, Alex, so you mentioned, I mentioned that you are the technical lead of robotics at CACI. So what is CACI and what is your relation with NASA?
Yeah, great question. So CACI is a support contractor to NASA Johnson Space Center. So when I say support contractor, think of a NASA project in robotics need an engineer with a certain skill set. They'll reach out to a support contractor like CACI for an engineer with that skill set.
Okay, okay. Yeah, so then it's an external company that works for NASA. That,
Correct. And so I'm co-located with NASA engineers or NASA civil servants and other support contractors on site at NASA Johnson Space Center. But we're all
uh,
a pretty badge blind project, and so can't really tell who works for who. We all work together in a collaborative manner.
okay, yes. So, okay, I'm curious about that because never work in this way. Well, actually, no, now that I think, yes, I was sometime. Yeah, so so it's like you are part of the NASA team, but your mother company is another one, but you are at the Johnson Space Center working with
Hmm.
all the other engineers from the NASA and from other companies also.
Yep, I think you've
Okay,
got it right.
okay, got it. I understood. Well, that has to be awesome to be there and to showing all the projects. And what about you, Misha? Is the same situation from a different company?
Yeah, exactly. My company focuses a bit on other types of tasks, but CI and METECS overlap, kind of in the robotics area, which means that I handle more of the software side of things, and Alex handles more of the hardware side of things.
Okay, and your company is called METEX,
Yes,
your mother company, the one that is let's say is doing the paycheck.
right.
Yeah.
Okay, okay, great. Okay, now I understand the structure. Um, I know I'm asking those things very basic for you, but for us from external, this is we don't know how it works, and it's very interesting to understand this kind of dynamics and how to is this works. That's why I want to clarify. And then Alex, so what does a technical lead of robotics do? So what is a typical day of your work for you?
Yeah, so I'd say maybe a quarter to a half is dedicated to mentoring or assigning tasks. So, like Misha mentioned, I'm more on the hardware side of things. So, within the Dexterous Robotics team, we have hardware engineers, so electrical engineers, firmware engineers, mechanical engineers, and whatever we're working on, I'll be kind of the person above guiding the tasks and making sure that in any integration efforts that we don't miss anything, and that everyone within the hardware side of things on the team is getting the job done. And then the other half is doing actual technical work. So I get the opportunity to jump in and design printed circuit boards, write firmware myself, and integrate with the mechanical team and the higher level software team as well. So that's um, a good part of even being in leadership. You still get to do technical work.
Nice. So you achieve to have this balance, which for managers is very difficult because you are an engineer, right?
Yep.
You are an engineer, in the sense I don't know exactly on the degree, but in the sense you are an engineer, so you want to do engineer jobs, but when you progress on your career, then you get this situation where you have to lead a lot of people, and then you don't have time to do the engineering work, and it's different to balance. So it looks like you kind of manage to do this in this project.
Yeah, and we have a relatively small team as well. So to the capacity that I can, keeping everything organized, I take every opportunity to get down and deep into the design work too.
Okay. Okay, great. Awesome. And what about you, Misha? So are you in the same situation as Alex?
It's very similar, actually. About 50% of my time I spend in terms of just organizing the team, figuring out kind of the next steps of the development and the necessary parts of the integration. Overall, kind of trying to ascertain the best ways to change the software architecture for future demonstration and development. And about 50% is actually working on specific algorithms and capabilities to integrate into our robots. It's very similar, and because we're a small team, like Alex said, things tend to be like, you think about it, but you also have to write the code, right? Yeah, there's
And that's awesome.
yeah, no,
That's very cool.
it's amazing. It's also, I think we also do a lot of the testing as well, both Alex and I. So we we design stuff, we write stuff, and then we also test stuff. All kind of part of the process.
Nice, nice, very good. And are you working together on the same space at
Yes,
the same space? Yeah.
yes, we officially our desks are on different floors, but we visit each other constantly. We communicate clearly. We, aside from the weekly meetings, we also stop by each other's table and ask each other's opinions usually.
Okay, okay, great. Okay, yeah, just to clarify, because now we can see that you are in two different backgrounds
Mhm.
for this, and then so we can understand more or less how this kind of works. So, to let me summarize for the audience. You are working developing the robots for NASA, and then you have two main teams: the hardware team, which is led by Alex, and then the software team, which is led by Misha,
Mhm.
right? And then you of course you have to work together, because otherwise it's not like in the earliest days of robotics that, oh, I'm doing my thing and I'm doing my thing, and then at the end I don't know how it's going to integrate. So we have to integrate from the beginning, right? Otherwise it doesn't work.
Exactly.
Yeah, okay, great. And then, okay, then let me ask you one question. Now that we have understood your roles and how everything is working, so what is the role of robotics for NASA?
Yeah, I kind of put this into maybe three different groups here at Johnson Space Center, at least. One is we have a few robots for testing. And so I think I might touch on it a little bit later, but there's the Active Response Gravity Offload System, or Argos. And there we test with astronauts inside for different EVA or extravehicular activities scenarios. So the astronauts are within the robot and then are able to test the different scenarios where they might find themselves inside the space station or on the moon. We can go into a little bit more detail on that later. Then another group of robotics is for operations, and that's probably more where the Dexterous Robotics Team fits, operations and research and operations, where we come up with concepts of robots that we can deploy maybe on the moon or on a space station, and then prove out the capabilities, and then hopefully, like in the case of Viper, which is a lunar rover going to the moon here pretty soon, deploy it and start operating on the lunar surface, and hopefully find the ice that we're looking for and do some science. And then the third one is STEM, or science, technology, engineering, mathematics outreach. So we have a lot of mentors here within our robotics group at NASA, mentoring high school students in FIRST robotics. And so we're using our expertise in robotics to show high school students in competitions kind of the way that we design robots, and give them some advice, and hopefully inspire them to go into a career in robotics later on in their lives.
Nice. So okay. So that blew my mind, because I had no idea about this clarification. If I have understood, there are three ways that robots are important, are used for NASA. First one is to use robots for doing things for it in the experiments that NASA has to do, but
Mm-hmm.
on Earth.
On Earth,
So you
yes.
use on Earth. So it's robots that are doing manipulation of things that you need to be done by somebody. So the experiments here and the practice of the astronaut or whatever you need to be done is done by robots. So this is the first one.
Yep.
Then the second one, which is the one that everybody imagines, is the robots that go to space and then explore the environment.
Mm-hmm.
And then the third one would be educational robots, in order to teach some young scholars and and
Yes.
make them
Yeah.
learn and also inspire them.
Yep. High school students, college students. We have visiting researchers that come and use some of our robots here for some of their research and development. So there's a lot of avenues where we get to reach a younger audience and inspire more STEM STEM
Okay.
careers.
Awesome, very good, very good. I had no idea. So in my mind is okay. I was asking this question because I wanted to clarify, but in my mind it was okay. We have robots that go to the space, to other planets, to the spatial station to do things there. But I didn't think that whole broad spectrum that you have here. And how does NASA envision the future of robotics? So for which users will NASA think that the robots will be important in the exploration of space?
So I guess a great example now is to bring up Viper. So the Viper lunar rover is going to the moon in the near future, and then we'll be looking for ice on the lunar surface. And we can look at the content and percentage of water on the moon, and then use that for future missions. So robotics plays a key role in any sort of science endeavors that NASA has. And then as far as Johnson Space Center goes, this is the Human Spaceflight Center. And so a lot of the robotics done at Johnson Space Center is human oriented or human centered. So whether it's human operators or robots that are meant to operate in the same environment as humans, that's kind of our niche or our goal here. So some examples there is Robonaut or Valkyrie. Those are two of our humanoid robots. Both are made in such a way where they can be cobots in a way. So you have a human in the same environment as the robot, and it's able to safely interact with that human. And I can go a little bit deeper on the technical side of things about that a little bit later if you're curious, but they're safe to operate around humans. And then on the operations side, you can have the humanoid form of the robot and then intuitively control it via virtual reality. And so some of our envisions are, say you have an astronaut inside a habitat and it's not safe for them to go outside into space. You have a humanoid robot that they can remote into it and then start doing the job that they were trained to do, but from the safety of the habitat. And the humanoid form, you can kind of think of, see what the robot sees, and then you lift up your arm, the robot lifts up its arm in a similar manner. And so there's not too much more training necessary in order to operate it. It's more intuitive for the user.
Awesome idea. Also, I didn't think about that one also that you mentioned about the remotely controlling the robot from within the, let's say, for example, in the space station, an example, or it could be on the moon if there is a base camp and then the people is there inside the base, but you need to do some operations outside, and then it takes a lot of time to an effort, and maybe it's even dangerous to go. So you can send the robot, which is teleoperated from the inside. So the latency is almost non-existent because you're very close, and then you can command that robot. Oh, that's very cool. But you mentioned sorry, say.
Oh yeah,
Go ahead.
exactly. And I'll take the opportunity to say it's a lot more than just space applications where something like that could be useful. So I'm not sure if you're familiar or tuned into the ANA Avatar X Prize recently.
Yes, some weeks ago, right? Yes.
So I think just from there you can see a bunch of different applications of this sort of teleoperation of a humanoid robot, but in terrestrial applications. So we have some partnerships with different EOD response agencies and commercial partnerships, where essentially you have operators that are putting their lives at stake, going out into the field to do something, but instead you can keep them safe, and then they can still operate the robot, do what they're trained to do, but from a safe distance in a safe location.
Exactly. It's this is again is the same situation in which something that has been developed for the exploration of a space, then it's afterwards is found and used in the local here in our vicinity, close to us. So it's something that is useful, right? Like for example, they say, but I don't know if it's true, is the Velcro. You know, the Velcro is the Velcro for closing without this one.
Yeah.
So that's something that was invented for space, but that's what I heard. And then, but then it's super useful here on Earth. So the same applies here to the robots that you are designing and the teleoperated robots there.
Yeah, exactly.
Right. It was also used, ROS was also used on Robonaut, but Robonaut was more like experimental robot, right? It was not doing actually something that was required to the success of a mission for exploration, for the tasks. It was more about doing experiments with robots on the space station, isn't it? Am I right?
I mean, generally yes. So you know, it was a humanoid robot. At least the apoptosis was, and the goal was to be able to operate human interfacing with anthropomorphic robots. And it was fairly successful. We were able to essentially put it in the space station, able to perform some tasks, and at least the initial part of the Robonaut mission was successful. I think it's it's a step in the direction where robots are able to perform specific activities, especially maintenance of stations by themselves. Yeah.
Exactly, it was going into that direction. So you were doing the early experiments, right, in order to go into that direction with Robonaut.
Right, and if my memory serves, a number of papers were published from the work that Robonaut was doing and went back into us. I think there is a quite a strong strong history between ROS control and R2. Some folks were really heavily involved with it, and a lot of experimentation was taken as it was being developed.
Okay, okay. And can I ask you what is the current status of Robonaut at present? So is this still on the space station, or did it came back to Earth?
So Robonaut 2 came back to Earth. The I think we had plans to put it back on the station, but unfortunately, I think in 2018 there wasn't there wasn't a place where to put the Robonaut. So unfortunately, it wasn't. We weren't able to deliver it back on the station, both the upper and lower half. So yeah.
Okay, 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 okay. I understand. And then let me ask you another question here on my list. And so Alex, you have mentioned about remote controlling the robot. Then can I say that then NASA is more directly directed to create robots that are that have shared autonomy with a human rather than completely autonomous robots, or which one?
Yeah, great question. So I'll revert back to we're located at NASA Johnson Space Center, which is the human space flight center, and so there definitely is a push for incorporating humans and astronauts inside our robotics here. So I can't speak for other NASA centers and how how autonomy goes into their robots, but here we definitely plan for shared autonomy. Whether it's controlled by an astronaut, controlled by a ground control station here on Earth, and to what extent we have a human in the loop. And then we definitely are doing research in different levels of autonomy, but our core nature here at Johnson Space Center is to be centered around human spaceflight.
Okay, okay, and then this shared autonomy you mentioned, it could be done by the astronauts themselves, or even from the Earth control.
Correct. That's the intent. So I'm actually sitting here in the Robonaut Control Center, which is where we sent commands to Robonaut when it was on the International Space Station. And then in actually the picture behind me, you can't really make it out. And then for those of you who are on audio, there's a picture behind me of an astronaut inside the VR system, standing a few feet away from Robonaut on the International Space Station, and then controlling it with a VR interface inside the space station. So those are kind of two examples of both. And I'll speak kind of quickly on maybe one example of autonomy that we have. So we've moved on from Robonaut as our main hardware platform for software development to Valkyrie, which I believe you might be familiar with. And
yes,
at least when I look up on the ROS Developers podcast, it puts a smile on my face to see Valkyrie, or 3D rendering of Valkyrie, which is our bipedal humanoid robot.
yes,
In the
logo.
podcast logo,
Yeah.
yes, or in the thumbnail. So right now, Valkyrie is our main humanoid hardware platform, and one example of a autonomy feature that we have is waypoint navigation. And so the idea there is, instead of specifying the exact places that you want to put your feet, you can point and click some distance away, and the robot autonomously plans a path to get there. So
that's an example of shared autonomy, right? Because
correct.
The robot itself is not deciding where to go, but how to go to the place that the person has indicated, right?
Exactly.
Yeah. So the robot, it is able to autonomously decide where to put the feet, how to avoid an obstacle. So you don't have to be controlling every second the robot. You just say to the robot, go to this point because it's the interesting point for us, for investigation, for grasping something, whatever. And then the robot decides how to reach that point, right?
Exactly.
Yeah,
Yep, you hit it on the head.
I think kind of that focuses on our philosophy in terms of development of these autonomous features. We start with a very good basis for being able to do stuff, locomotion, manipulation, those things. If we can do them well, via teleoperation, we can also develop frameworks around them to support autonomy in order to ease some, cognitive resources of the humans that operate with the robots, um, striving towards more and more autonomy.
Yes, yes. And also you mentioned another, Misha, you mentioned another example, because the going to the point, to a place is very clear, but another one very important is to grasp something. So when you have full control, teleoperation of the robot, you have to be trying to move this and trying to grasp from your limited perception, because you are not on the, but you can say now to the robot, grab that thing, and then it would do it.
Exactly, and even taking a step before that, even if you want to grab a specific thing, with mobile robots, it's very important when how to approach an object in order to grab it, and being able to automate the selection of poses to grab objects incredibly helpful in order to facilitate those kind of activities, right? And that's something that we focused on earlier last year and earlier this year, and with a heavier focus next year in order to kind of build upon that and do more complex manipulation.
Awesome. Do you have any video that you have released about that that we can point to the audience? We can point the audience to. Sorry, my English.
So I believe we have a number of videos. I think we're working on getting them, export control, getting them out of NASA's essentially firewall into the public in order to show this kind of progress.
Okay.
So yeah.
I understand. Just asking, just in case that it's available. If not available, it's completely understood. This is your research and your project, and then you will decide when to do it. In any case, if in the future you release those any video or document related to those subjects or any other that we are talking here, please feel free to contact me so I can pass to the audience, and they will be very happy to see your progress. I'm pretty sure.
Of course, yeah.
Okay, and then let me ask you, then Alex, about this system that you have already mentioned before, the Argos one, which I think that this will be included into the first type of category of robots that NASA is using, the ones that are used for doing experiments, so to doing tasks. For NASA doing tasks. Can you tell us what is the Argos system?
Yeah. So this is a very exciting robot for me. I got a chance to work on it a few years back, but it's the active response gravity offload system. So the keywords there are gravity offload system. So the idea there is you want to simulate a specific gravity setting. So the robot enables us to do so as long as it's a gravity setting between 0 gravity and Earth's gravity. So the way the robot works is you put a payload, sometimes the payload is an astronaut, inside the system. And there's a long cable that goes about 20, 30 feet high that goes up to the main robot. So the cable is coming down and it's connected more or less to the payload, to the astronaut. And think of a winch or a motor that winds up the cable that offloads or pulls the payload up. So whatever gravity setting you have it on, there's inline load cells that sense the force in that Z direction of the payload. So think you are standing on the ground, you jump straight up. It senses what force you're jumping straight up with, and then communicates that to the control system. And then the control system winds up that winch to pull the astronaut up. And it pulls the astronaut up with whatever acceleration that gravity setting gives you. So if you are simulating the moon and you're inside the Argos system and you jump up, you're going to experience 1/6 gravity. So you're going to jump really, really high. And there are some videos released if you type in Argos, so ARGOS, in YouTube or Google or something like that. Make sure you include NASA, because I think there's some other nomenclature that Argos was derived from. But you'll be able to see some videos of some celebrities or test subjects and maybe some astronauts inside the system. But the main use here is we can test a lot of different things, from spacesuits to actual test runs of extravehicular activities that astronauts are going to do within the system. So yeah, pretty much every day, every other day here at NASA, there's some sort of test going on inside Argos, and I'd say it's essential for our missions here.
Wow, it's awesome! It's awesome, this system. Have you tried yourself?
I have, yes. So I was in it in the 0 gravity setting. And so in that one, you're kind of laying down like Superman, and you grab something and then you pull yourself, and you're going to keep moving at that constant velocity until you grab something else to stop your momentum. It's pretty cool. I think probably the closest I'll ever get to actually being in space, but it's definitely a great robot.
Okay, we'll see. We'll see. You are very
We'll
young.
see. We'll
yes,
see.
exactly. We'll see. We'll see. Wow, awesome. And here, well, probably you already thought about it, but this is another example of a technology that you can produce some other benefits outside of the space exploration. For example, you can sell this technology to Hollywood, for all those movies that do those very bad movies that they did, the gravity on the moon, and they do those jumps and very ugly, very badly done. So I don't know.
Yeah, there's a lot of different things that you can think of, and actually we've put some of our robots as payloads inside Argos. So Robonaut, whenever we were doing testing for legs on Robonaut so that it could navigate throughout the ISS, well, how are you going to test a robot moving in space with 0 gravity? So we used one robot to test the other robot in as close as we can get to a 0 gravity environment.
And do you know if this is it possible for third parties to book some time on the Argos and do experiments in there? Is it possible, or is only a technology for NASA?
I'm going to defer here that I'm not on the team currently, so okay. I don't know who the customers of Argos is, but I know they're doing a lot of testing. So.
Okay. Yeah, it's just a question that popped up in my mind right now, because I think that would be very, very interesting, for example, for testing robots that you mentioned, about robots that should operate on space. And there are those robots, I don't remember the name, that are the cubes that are cubes that are floating on the space station at present.
Astrobi, yes.
Astrobi, exactly. So maybe that's a way of testing this kind of robots before sending them to space, because sending them to space and then debugging there is a lot more difficult. So for other companies, maybe that they are developing kind of robots that should work on space, maybe that would be interesting to rent some time on Argos. I don't know. So just an idea, if somebody of NASA is listening and is thinking about business models of this, so I think that would be interesting. Oh, awesome mug of NASA, the mug that you are using, awesome.
Oh, thanks. Yeah, I love it.
Very good. Okay, so and then you mentioned about the Valkyrie robot, humanoid robot of NASA. So everybody in the audience know about it. If not, I will put a link on the show notes. If you don't know, it's a human-sized humanoid robot that was developed by NASA. So what were you doing in the project? What was your role?
Yeah, so we've mentioned previously that I've been more on the hardware side of things than I'd say higher level software. So I've designed motor controllers, so printed circuit boards that are meant to get a motor to spin. And then you can think of the robot as one motor per every degree of freedom. And Valkyrie has 44 degrees of freedom. So we have a lot of motors there that we need to get to spin. So there are motor drives that drive each one of those motors. And there are different control methods that get those motors to spin the way we want them to. So you can think of direct current control, position control, but in the scenarios where you have a human in the environment with the robot, generally you'll have a torque control or impedance controlled actuators. And so I'll write firmware, or I've written the firmware for the torque control and impedance control actuators so that Valkyrie can operate with with humans. On top of that, I've written some kind of, you can think of it as middleware or software that takes the high-level commands, maybe like the waypoint that you send to the robot, and parses those into the low-level commands that we send to each of the motor controllers. So there's a piece of software that kind of decodes trajectories or decodes those waypoints into torque and position set points, and then forwards those out to each of the microcontrollers that are running the firmware that actually perform the motor control.
Okay. Okay. Yeah. So yes, of course, as in your team, in the team that you are, which is closer to the hardware rather than
Right.
to the software part.
Right.
Yes.
So I think at a high level, I work with everything below the generally accepted ROS layer. So whatever's running in the ROS nodes, they'll communicate down to the hardware.
Exactly. But for that, we have Misha here on the
Yep.
podcast. And so what have you been working on Valkyrie?
Yeah,
Misha?
so I basically take all of the hard work that Alex is doing and I build on top of that. So any higher level system is essentially my domain, from integration of different system like perception, motion planning, task planning, as well as the integration of that with our VR interface, which we usually use for controlling Valkyrie. Also the development of kind of utilities in order to alleviate some of the human interaction with the robot, right? We want to have Valkyrie accomplish its mission as fast and as easy as possible on the person. So developing those tools, like I mentioned before, knowing where to stand in order to manipulate the object, ability to identify the object and know what the object is and manipulate it well. The integration of those components is within my domain, which is where we use a lot of ROS in different ways. Yeah.
Okay, so ROS is inside the Valkyrie for doing some of those tasks that you mentioned.
Right? Absolutely. Yeah.
And then what is the role of simulations for that? So are you using actively simulations of Valkyrie?
Yes. So we have a couple of simulations that we use. Most of the time we use it for testing and verification of our algorithms. Because of the way the architecture is structured and our kind of vision to the future, we want to be able to make sure that the components themselves work very well. So as we develop, we test it inside of a simulator. We make sure that the robot behaves as it should be, right? Because Valkyrie balances and stands on herself. Our algorithms have to make sure that we don't accidentally make her fall and break some of the hardware that Alex is going to be mad at me over. So we usually use the simulators to make sure we avoid those pitfalls, to make sure that the system is communicates well and is properly the topology of the system is all good, and then we test it on the robot after we have a good estimation of our efforts.
And are you using Gazebo as the simulator or any other simulator?
We're using Gazebo for some aspects, and we also use the SCS simulator from
Which one?
SCS from IHMC.
Okay, SCS. Okay, I don't know now for that one.
Yeah, it's if you Google SCS, IHMC, those two acronyms, you will be able to find a pretty robust simulator for specifically focuses on bipedal locomotion.
Okay. And especially the physics of the interaction with the ground and the joint maybe is because of that.
Yes, they have not to talk too much about specifically the simulators, maybe a little bit beyond what of my focus,
Okay.
but
I understand.
locomotion is typically the specialization of that simulator.
So, what other projects related to robotics have you been participating, Alex? And any other robots that are being developed at the present? You mentioned the Viper also, and you mentioned the Argos and the
Yes.
Valkyrie.
Yeah. So I've worked, me specifically, I've worked on 3 robots. So Argos and Valkyrie being 2 of them, and then the third one actually for our for more astronaut training or testing. There's a cable robot, so it's going to be hard to picture for our audio audience, but you can think of a cube robot with tendons or strings attached at every corner of the cube, and there are motors at the end of those strings. And with those 8 motors, you're able to control the cube in all 6 degrees of freedom. So your XYZ translation, and then your roll, pitch, yaw orientation. And so there you can have precise 6 degree of freedom control on this cube. So we take the cube and then put some very precise force torque sensors on the cube, and have astronauts push on those force torque sensors. So we can sense how much force they're pushing with, and then we can call the cube any sort of mass in space. So you can think of, well, I'll say in space, since there's no gravity, you can move something that's really, really, really big just by pushing on it. And since you're in 0 gravity, it'll start moving. Based on the mass and inertial properties of the object, we can program that to be whatever that cube is, and simulate handling the mass as if you were in space. So you have the astronaut pushing on this object, pulling on this object, exerting a torque on the object, and the object, or that cube, the robot, will move in such a way that it feels like you're moving a mass in space. So think of if you're outside the space station and you have to grab an object and move it from one place to the other, it's going to move in a different way than you would expect it to, because you're in 0 gravity. Yeah, exactly. So this is a way to test that, because we have a simulation running in the background that would simulate that mass and that inertial property as if it were in space, and then it will command the robot to move as if it were in space. So
okay.
that's another one.
It's a testing device for here in Earth to simulate the behavior of objects in the space. So the astronauts, they can be practicing how it will be in space to grab things.
Yes, you put it better than I did. So
no, you explained it very well. You explained it very, very well. So I was able to capture the picture, and then I'm explaining in my plain vocabulary.
Yes.
Well, you explained beautifully.
Great job.
Okay, awesome. Do you have any images of this that are public?
I think I'll say, if you Google the virtual reality lab.
Virtual reality lab, okay.
Yeah, at Johnson Space Center. There might be some images of the system there, but no guarantees.
Okay. I will look for that. Okay, I will look for that and put it where I find on the show notes of this episode. Then okay, so now it's a question for Misha. So what can you tell us about Space ROS? You know that recently it has been talked a lot along this year, actually, about the Space ROS, the ROS2 version for space that is being developed by Open Robotics, Blue Origin, and NASA itself. Can you tell us something about it?
Yes. So
what it is, what is the status,
Sure,
what is
thank you.
the purpose?
So Space ROS is an unfunded agreement between NASA and other commercial partners in order to facilitate kind of the development of ROS for utilization in space. What that means is that we want to make sure that ROS is certified for all of the systems and that we can essentially run ROS things on in space. Pretty simple. So the goal for this is to be able to lower the barrier of entry of cutting edge technologies that are being developed in the ROS environment in order to essentially help out with the mission, with NASA's mission. There's quite a lot of work that's being done just in the ROS ecosystem that it would be very useful for the mission, and this is the program that tries to lower the barrier of entry of these technologies into our ecosystem, essentially. That's kind of the brief overview, and kind of I think certain aspects of this of our desire with Space ROS is to make sure that it's not a separate version of ROS or ROS2, right? We want to be able to facilitate both the development of ROS as well as the integration of technology without having kind of like a separate closed version. This is more kind of to allow an easier way to get technology certified for space operations.
Okay, so if I have understood correctly, then NASA wants to use ROS because there is a lot of cutting edge algorithms being developed by third parties around the world and that are could be very useful for you. So it could speed your development, but then you cannot just bring this code here because NASA has a very high, the super highest level of.
Yes, of course. The number of redundancies and safety checks that you have to pass is not something that the usual developer takes into account.
We
right?
do.
Yeah, and we hope that Space ROS can help us collaborate on the robotics problems that every robotic researcher tries to solve, and essentially push our technology forward as fast as possible. This is just one of the avenues we're exploring in order to kind of facilitate the infusion of our partners and their expertise into space.
And can we expect any release for the open public of this Space ROS? So it's going to be openly published, or is going to be only used for NASA? Within NASA.
I don't necessarily have the full information on that.
Okay.
Yes. Sir.
Okay. No problem.
Yeah.
Just asking because I don't know. So probably the audience is very interested to see. Oh, I would like to try this and this is a project that has started like this year, if I'm not wrong, right? It started at the beginning of this year.
I think beginning of this year, and I remember hearing talks about it late last year. In general, there are a number of hurdles that we as engineers need to get over, but our aim is collaboration, right, with all our external partners. So that just keeping that in mind, that's kind of our aim with Space ROS as well.
Okay, so in case that you do any release or any news about the Space ROS, then if you want to contact me and let me know, then I will distribute also to the audience of the podcast, because I'm pretty sure they will be very, very interested to know more about the status of a Space ROS.
Of course.
And then let me go with the final question for both of you. So what advice would you give to the listeners that would like to follow your path? Because your job is awesome. You are engineers, you are developing robots for NASA. So I don't know if it could be something even cooler for an engineer. So developing robots, but not all robots for cleaning the room. That is cool. It's very cool. but for NASA, so many people is listening to this episode and say, oh, I want to be like those guys. So what do I have to do?
Well, I'll say, luck definitely has been on my side to have the opportunity to work here. But as far as my path goes, the main thing I've focused on, and this is consistent in all of robotics, is being multidisciplinary and understanding different aspects of engineering. And so although my core focus is in embedded electronics, so electrical engineering and writing the firmware code for those, throughout my career, I've focused on being able to speak the same language as the Mishas of the world, and then the mechanical engineers to make sure that my electronics are able to integrate seamlessly with their mechanical designs. And that's something I've always strived to do, is understand the larger system and how everything fits together, and especially being at NASA with all the complicated systems that we work with, that's definitely something that we look for.
Awesome.
Yeah, I can't agree more with Alex. It really helps to be very good at specific things, but the ability to understand the system as a whole, especially when you're collaborating in an environment, because engineering is a team sport. You have to be able to understand other people, their needs, and develop your technology to suit not just one specific task, but the entire team in general.
In your case, Misha, you have been working more on the development side, right, of the intelligence. So, from that side, what would you recommend the audience that they have to put a special attention, apart from this vision of integration, but from the software specific skills?
Software specific skills, I think understanding the fundamentals of building a good piece of code is incredibly important, right? Prioritization of different resources is something that you encounter when developing a robotic system, and ability to understand, like, for example, what type of algorithms need what type of resources is very important, and how different parts of your system communicate is I think would be a second point, right? You can make your system quite a bit more understandable, easier to use, and easier to iterate on if you have a very good approach in just designing the interfaces, for example, between perception and between manipulation. I think that's the key. Like, uh, the fundamentals are incredibly important, and I find that I try to take a problem and strip it down to its bare necessities before I kind of integrate it into a larger system.
Okay. Then thank you very much. I hope that those advices for the audience, they are useful, and some of them will be taken into account from people that want to work for NASA in the future. And thank you very much, Alex. Thank you very much, Misha, for being here. And then I don't know. So see you around the world, guys.
Yeah, of course. And real quick, we are definitely looking for anyone who's interested. So I think I'll hand it off to Misha a little bit more to describe about the types of developers, but we'd love to see our team grow.
Oh, awesome. So is this a job offer for the audience?
This is a call to action to call people to apply for jobs around Johnson Space Center
Okay.
for position. We're looking for all kinds of folks, but generally, if you have a good solid foundation of robotics and experience in writing good code, this is the type of person we're looking for. We're also looking for a lot of different people who are in undergrad or graduate programs to help us do some cutting edge research and development with our essentially hardware platforms. There are a number of programs like USRA and Instago that essentially allow you to apply and work with us on our robots at Johnson Space Center. Yeah, those are usually the avenues you want to look if you're looking to work for NASA.
Okay. Okay. Awesome. Any link, a specific link? Does it exist? So I will ask you for this on email. And
you can. I think one link that I can definitely share with you is this intern.nasa.gov, and if you look up Instagram and STGRO, that's another program that is we're very happy to work with.
okay, perfect. Then I will put all those links and information in the show notes of the episode. And I hope that you receive thousands of people asking to work with you and to follow this program.
Thank you so much.
Thank you very much. And see you next week with a new lesson from the experts. And until then, keep pushing your ROS learning.